Today, most archaeologists agree that shell rings represent the refuse of habitation or ceremonial sites where ancient Native Americans lived, ate, and celebrated important events in their lives. Though few rings have been studied, some of those that have do reveal evidence of wooden post structures, hearths or fire pits, storage pits, broken pottery, and bone and shell tools. But most of the ideas that shell rings represent living areas come from the assumption that the shell, bone, pottery, and other artifacts that make up the ring represent food refuse from daily meals. With few rings having been excavated, and data somewhat limited and often lacking, variation in the hypotheses as to how shell rings actually came to be have arisen. Some suggest that houses were placed atop the rings of shell, although no evidence of wooden structures has been found on the ring tops. This has led others, noting post molds and hearths within some rings' interior plazas, to suggest that the edges of the plazas were places where people resided. On the other hand, the observation that some of the central parts of the ring plazas often lacked shell and other refuse have led some to suggest that the rings were used as ceremonial sites where feasting and ritual discard was used to make the surrounding ring. Combining both ideas, others have suggested that the rings were places of both habitation and periodic formal ceremonies. Under these hypotheses, the specific use of each ring varied depending on cultural traditions and practice, and the specific place of the site itself within the political landscape. At larger, multiple ring sites, both specifically ceremonial as well as daily living rings may be found. At these sites, certain rings reached extraordinary sizes and heights, and were placed next to burial or platform mounds, suggesting that groups or individuals associated with them may have held special status. As opposed to social understandings of shell rings, some archaeologists prefer to think of rings in terms of their relations to the environment. One recent environmental idea links the development of shell rings to long-lasting periodic droughts, beginning around the same time as the appearance of shell rings. This idea suggests that coastal inhabitants suffered an increased need for fresh water during drought conditions. To remedy this presumed need, two environmentally oriented hypotheses have been proposed that suggest rings were simply practical contrivances to collect water. One suggests that shell refuse of daily living was kept separate from their living areas, and as people brought the shell from their villages to discard, they dug wells in the center of the circle to bring fresh water back to the village. The other suggests that rings of shell actually served as holding tanks to capture and hold freshwater rains or stream flow channeled into the ring. While no hard evidence has ever been found that supports the idea that shell rings once held pools of fresh water, the idea has caught on among those archaeologists who decry ceremonial explanations for shell rings, in part because it's one of the few environmentally linked explanations for the circular form of ring. To test the idea of shell rings as reservoirs, a series of experiments were conducted designed to determine whether rings have the capability of retaining pools of water. Archaeologists at the Southeast Archaeological Center of the National Park Service have been studying shell rings for over 30 years. The idea that a circle of shell could hold back a pool of water like a swimming pool was counterintuitive. Not only were shell rings generally open-ended features, but even with the few known closed circles, the large granularity of oyster shells seemed too coarse to provide an impermeable barrier capable of holding water. To examine the rate of water flow through piled oyster shell, SEAC staff conducted a quick test in their offices in advance of larger experiments to be conducted in the laboratory and field.
We're going to put, I've got this little container, we have two screens, and we'll put the shell in between two screens, and we can make those screens. We know how to do that here. And it's going to be made out of kind of a mesh. It has mesh, it has holes in it, but we'll make the holes a little bigger, chicken wire, and between there we'll fill this with shells like this, fill with oyster shell, and then we'll take, rather than pouring the water right in here, it'll all leak out like you were saying, we'll put in a piece of plastic, like this, to keep all the water in right there. And then we'll take the water like that, flow it into there. We got all the water there. None of it's leaking over there, you can see, because it's in plastic. And then when we're ready to do the experiment, all we have to do is just lift this up, let all the water fill in there, and it'll flow through over to that side. And that's it.
To increase the scale and measure actual flow rate through a real wall of shell comparable to the size and thickness of shell ring walls, the experiment was taken to the Florida Department of Agriculture's Division of Aquaculture located in Apalachicola. There, enormous piles of oyster shells resulting from local harvesting are maintained to seed the region's oyster beds. With the help of the division's personnel, SEAC staff constructed a ring of shell. Our initial goal was to make the ring about 10 to 12 meters across, line it with plastic, fill it with water, and remove the plastic to measure the drainage time, much like the office experiment but on a more measurable time scale. The question to be tested by this procedure was, could a ring of shell hold water for even a short time? Here the base of the ring was about 4 meters thick. To make the interior basin impermeable, we taped 2 tarps together to line the oyster shell basin and filled it with seawater pumped in from the adjacent dockside. Because the overlapping tarps were not perfectly sealed with the duct tape, some leaks occurred initially, but as the water pressure increased, the overlap of the tarps sealed the leaks and we were able to fill the basin to a depth of 65 centimeters, totaling 10.5 cubic meters, or nearly 2,775 gallons of water. Removing the tarps was harder than we had anticipated, given the tremendous water pressure weighing it down. We removed the tape holding the tarps together and pulled the tarps apart at the seam. We also pulled down the upper levels of the tarp where the water pressure wasn't as great. And finally, we pulled the tarps out little by little as the water levels lowered and the pressure was reduced. Although not a particularly elegant endeavor, the experiment did show that the water drained exceedingly fast, in part through the upper walls, but mostly through the lower walls and floor where the water pressure was the greatest. As this graph shows, 90% of the volume of water drained quickly in about 2 minutes, until it reached a point at about 10 centimeters in depth where the water pressure decreased and the drainage rate leveled off, taking another 5 minutes to drain completely. For our second experiment, we wanted to increase the thickness of the shell walls to see if the increased amount of shell would impede water flow through the shell to any significant degree. For this experiment, we expanded the diameter from 12 meters to 15 meters at the base, and the base wall thickness to 4.5 meters. With a larger single tarp, we were able to fill the water to a greater depth of 92 centimeters, totaling 16.8 cubic meters, or 4,430 gallons. Once we filled the ring, our plan was to cut the tarp in half and remove each side with the help of a backhoe. Here we start the clock ticking as we begin cutting the tarp on 2 sides. Not having even completed the cut, the drainage was sufficiently fast to have brought the water levels down 30 centimeters within 30 to 40 seconds to the starting level of our earlier experiment. As we finished the cut, the water pressure was too great and on one side the rope broke. Thereafter we removed the tarps by hand. At certain points, the water depths were called out to our man off camera recording the time. Despite our struggles removing the tarps, the rates of discharge from the first and second experiments were remarkably similar. At the 2.5-minute mark, 90% of the water had drained. Thereafter, the remaining 10% trickled out as water pressure of the pool was greatly reduced and the ground saturated. Extrapolating from our experiment, we suggest that a large-scale shell ring with an interior plaza base 30 meters in diameter, if it were impermeable, could hold 755 cubic meters of water. But since shell is not impermeable, 90% of the volume of that water would freely drain out in 6 minutes, with the remainder trickling out within 18 minutes. In a set of lab experiments, we subsequently tested if the rate of water flow through the shell ring walls could be reduced if we were to add a more impermeable medium to the shell. Shell rings are well known for containing little or no soil intermixed within their shell matrices, and no large amounts of silt and clay have ever been identified intermixed with the shell midden in shell ring walls. Occasionally, however, small amounts of sand have been identified. The question was whether or not less permeable media like sand, if added to the shell in a shell ring, would reduce the rate of drainage. To test this idea, we went to the Florida State University's Geophysical Fluid Dynamics Institute, where Dr. Ming Yi and his graduate student Hing Dai provided the answer.
Yeah.
And you have sand on top of the ground, and then the shell is on top of it.
Or this is the ground,
Oh, that's the ground.
and the shell sits directly on it.
In the first laboratory experiment, Dai determined that a column of water flowed through shell medium 4.5 times as fast as it did through sand. The second experiment demonstrated the flow rate in centimeters per second of water through three media: loosely compacted oyster shell, loosely compacted shell and sand, and compacted shell and sand, with compacted shell and sand 8 times less conductive than loose shell alone. But even compacted shell and sand was exceedingly porous, with a ring 70 meters in diameter being incapable of holding a meter-deep pool of water more than 15 minutes. Together, these experiments demonstrate that oyster shell can be placed somewhere between gravels and cobbles as being some of the most highly conductive natural granular materials found along the southeast U.S. coastlines. If shell rings were built to hold water, the builders chose their medium poorly. From these studies, we can conclude that oyster shell would have been among the worst possible readily available natural materials to construct an enclosed barrier capable of retaining a pool of water. As earth and dam builders well know, a combination of a core of fine-grained impermeable materials like clay or silt with coarse materials like gravel layered on the outside of the core to diminish the erosional effects of moving water is the best way to build dam walls capable of holding water for extended periods. However, to date, no known archaic shell ring has revealed any impermeable materials in its construction. The two primary materials found in shell ring walls are highly porous oyster shell deposits, and to a lesser volume, only marginally less porous sandy soils. From where then comes this idea that shell rings were built to hold water? One source of this idea is that today a few known shell rings can be seen holding puddles of water, or at least water-loving plants within their centers. But it's not the shell ring walls retaining the water, it's the high tides. As tides move in, water fills the ring, and the water has nowhere to drain until the tide recedes. But sea levels during the building of the shell rings were lower, and no rings were placed in the tidal zone to begin with. In fact, the idea that shell rings were barriers capable of holding pools of water is something of a red herring. Even if the ring walls had been made of some material nearly impermeable, such as concrete, they would still not have been capable of holding water. This is because the ground all shell rings were built on was made up of another highly porous material, sand. As our own field experiments suggest, much of the water in a hypothesized shell ring reservoir would have drained through the ground upon which it was constructed. Why were shell rings built on such well-drained soils? Well, mainly because people didn't want to get their feet wet. All archaeological evidence indicates that people used rings for terrestrially based activities, including food processing, daily meals, periodic feasting, and refuse discard. These events likely involve visits from neighbors and guests, ceremonies, celebrations, and special ritual events associated with marriage, death, trade, and other social exigencies. Did low sea level or fluctuations in sea level cause droughts and a need to trap and conserve water? Maybe. But if so, shell rings would not have presented a viable way to do that. We do know that oyster habitats require substantial freshwater inflow into marine waters, and thus shell rings, which are constructed of monumental numbers of oyster shells, seem to have been constructed at precise times when freshwater flow into estuaries was sufficient to allow for the abundant growth of oysters. In either case, there's no doubt that environmental conditions tell a big part of the archaic shell ring story. The impetus behind the shape of the rings, however, is most readily explained from cultural perspectives.